Hey class, as you know, this chapter's material is completely extra credit. This is chapter 14 of your textbook. So the lecture, the activities, the quizzes, the lab, that's all gonna be extra credit. So just bonus points for you. So in this chapter, which again is chapter 14 of your textbook, we'll be looking at impacts and extinctions. The image that you're seeing on the slide here is a timeline that's showing you the extent of the whole Phanerozoic eon. So if you guys remember the geologic timescale somewhat from chapter, I think, 1 or 2, geologic time is split into eons as the biggest subdivision, then you have eras as the next biggest, then you have periods, and then you have epochs. And within each epoch there's a subdivision even as well. So epochs are the smallest unit of time. So for example, only a few million years, whether eons are going to be on the order of billions of years many a times. So the last eon that we have is the Phanerozoic eon, which we're still in, and that means new life. And so within the Phanerozoic eon, we have the Paleozoic era, which goes from the Cambrian to the Permian. We have the Mesozoic era, which goes from the Triassic until the Cretaceous. And then we have the Cenozoic era. So these other subdivisions, as you're seeing them before the Cenozoic, these are all periods. Okay? So these are periods from the Paleozoic until here, and then these three are periods from the Mesozoic era. Okay. So the figure itself also shows the number of genera of living organisms that were currently at a specific time in geologic history. So as you hopefully remember, life in geologic history has been, on Earth has been here for about 3.5 billion years, so a long time. But it wasn't until the Phanerozoic eon that life actually thrived. So conditions weren't quite right before the Phanerozoic eon for much of life to be as fruitful as it is now, or even not quite as fruitful as you're seeing here. This is today, this is before, but there was still a lot compared to how much there was before the Phanerozoic eon. So again, number of genera are exemplified by the green line, if you would. And also within this curve, you see that there are sharp declines in the number of genera, or rather there are rapid extinctions of a large number of living organisms on Earth. So for example, here things seem to be climbing, and suddenly a large number of species or a number of genera fully declined. They went extinct. Same thing happened here. Here, this is probably the biggest one that there was. Here, and then smaller ones kind of in between, as you're seeing as well. So in case you don't know what genera is, so if you remember from biology the subdivisions in taxonomy, it goes kingdom, and then I think it's order, and then class, and so on and so forth, until you get all the way to species. So species is the smallest subclassification. So for humans, we are Homo sapiens sapiens, which means that our genus or genera is Homo. So sapiens sapiens makes the species, but Homo is our genera. Before Homo, we are part of a family that is called the hominids, I think. So that kind of gives you an idea. So this is not particularly species, but the next level over. Okay? So as you see, and as I have sort of said, there were 5 major extinctions of life on Earth. In the graph here, they show you 6, but in truth, there were 5 major ones that we speak of. This last one is very small, and so many people don't acknowledge it as such. And some other people actually group the first extinction and the second one kind of together because they were a long period of sort of change in climate. And so it depends how you look at it and which papers you read, but there are 5 major ones that are talked about. The last huge or massive mass extinction, if you would, happened about 65 million years ago. So right here at the end of the Mesozoic era, We also call this boundary the KT boundary or the KPG boundary. So K is for Cretaceous, T is for Tertiary, which is the next period over, or PG, which is for Paleogene, which is the same idea, sort of. So the boundary right there at 65 million years ago is probably the mass extinction that we have heard about the most, because it's when the dinosaurs went extinct. But as you can see, some of the other 4 major extinctions actually took a greater number and percentage of genera off our planet. So for example, the third one, the extinction that happened in the late Permian, took, I think it was between 80 and 85% of the living organisms that we had on Earth. So that gives you an idea of how massive these things can be. So in the remaining of the chapter, we'll go ahead and examine these extinctions as well as one last one that is not outlined within here. And we'll also look at impacts on Earth. So by impacts, we mean like meteoroids or asteroids or comets that have impacted the Earth, and what the repercussions of their impact could have been on the Earth's processes, as well as any potential mass extinctions. So I hope that you enjoy it. Stay tuned. Okay, so before we get into the nitty-gritty, we're going to go ahead and look at Earth's place within space. So hopefully, as you should know, the starting point that we know for our universe to have started at was about 14 million years ago. Some people say 13.9, but about 14 overall. So this huge explosion, hopefully you know, it's called the Big Bang. It produced the atomic particles that we're later going to go ahead and form the different galaxies, the different stars, and the different planets of our universe. So stars started forming all the way since the first million years after the Big Bang, and they continue to form even today, which is pretty amazing. So the life of a star as we know it is highly dependent on its mass, mostly, but it's also dependent on its composition a little bit. But overall, large stars will have greater internal pressure, will have greater internal pressure, which will cause them to burn up more quickly than smaller stars. So overall, large stars tend to live less. Typically, stars that are about the same size as the sun, which is relatively small, will last about 10 million years. So that will be the life of a star about the same size of our sun. But any stars that are, say, 100 times more massive than the sun will only last about 100,000 years. So much, much less. So, given those numbers, our sun is currently close to being in the middle of the extent of its age. So, the Earth itself, as you are seeing here on the slide, is about 4.6 million years ago, and the Earth formed shortly after our sun was formed. So the sun is not much older than the Earth. And if we said that 10 million years is what we estimate our sun's life to last, then we can think that it's about halfway through its overall lifespan. Okay, so whenever you have more massive stars die, they will do so by basically collapsing inward because they can no longer sustain their mass. They're just too big. And so when they do this, when they collapse inwards, this is called the supernova. Okay? This results in what is a high energy explosion that typically scatters its mass into the void of space, and it creates a nebula. So what you're seeing in the image in here in the slide is a nebula. So it's what happens after the supernova explosion occurs. It scatters the mass into the space, and it looks something like this, like a nebula. So eventually, through gravity, the matter within that nebula begins to collapse back inward on itself. So all of that mass that was here, scattered after the supernova, slowly starts to gather together from all sides back to its core, if you would. And that is what will form new stars. So this is referred to as the solar nebula, which is also how our sun formed close to 5 million years ago. Okay, so After the solar nebula, our sun then grew by accretion or addition of matter that was part of the flattened pancake-like rotating disk, which formed by the rotation forces from that solar nebula. So that disk that again had a bunch of matter, much of that matter started being added to the initial part of the sun, and that's how the sun acquired more and more mass. So that disk, again, that pancake-like disk that formed at the solar nebula, was dominated by hydrogen and helium molecules mostly, along with trace amounts of other elements that make up our periodic table. So lithium would be the next one, so on and so forth. So as the solar nebula started to condense, the sun, which again makes up about 99.8% of the solar system's mass, so it's most of the mass from our solar system, it formed in the center of our solar system, again due to gravity. So most of that mass went towards the middle, which is the sun, making it the most massive part from the whole system. The remaining mass became trapped in solar orbits that were like rings, so similar to those around Saturn today. Some orbits, went around the sun, and that's where some of the mass got trapped. So the gravitational forces from the largest and the densest particles attracted other particles in those rings until they eventually collapsed into the planetary system that we have today, meaning that mass that was scattered throughout those rings eventually collapsed onto itself, making planets that were circling the sun as it is, or in some cases where just a bunch of rock masses that still orbit the sun in a rather disparate manner, like you're going to see in the asteroid belt later on in the lecture. So all of the planets within the solar system, including the Earth, were then bombarded by extraterrestrial objects ranging in size from dust particles to even some kilometers in diameter. And those made the size and the mass of the planets much larger, because as they were being bombarded, they got stuck to that massive organism, or not organism, but rather that body. So they got larger as the bombardment of this dust or kilometer in size particles continued to hit them. So although that bombardment has reduced in frequency and also in quantity since about 4 billion years ago, it hasn't really stopped completely. So it continues until today, but again to a much lesser rate. So again, all of the planets formed with the sun a little over 4.6 billion years ago, and they continue to be bombarded for the first half billion years or so at a great rate. After that, they still continue to be bombarded, but not nearly as much as they used to. Alright, so currently there are still trillions of particles that remain within the solar system. And these are typically grouped by their size and also based on their composition. So they start at interplanetary dust, which is only a fraction of a millimeter in diameter, to about thousands of kilometers for some asteroids. Again, that's excluding the planets themselves. So if you want to, you can refer to table 14.1 that's in your book for a detailed explanation of each type of body and how big it is, or what composition does it have to have. Here we'll go through some of those particles and their sizes and compositions, and also their characteristics, but not through all of them. So table 14.1 has all of that in detail if you're curious.